Okay, now, so we're gonna go into the Excel sheet. Let's assume that you have the information about your cumulative sales as shown in column C. In column A, this is just the year. Let's assume the T represent, or maybe months, the number of months. NT is the cumulative sales up until month 16. Now we want to find, the sales per year. So this is gonna be just that 4.9 because this is the first year, and you've sold 4.9 units. Next, this is just gonna be 9.2 minus the previous year's sales. So this is just 4.3, and you can just copy everything down. So this is basically 87.1 minus 82.6, which is the sales that you have in that year. Once you have that set up, then these three parameters will be the one that you want to estimate the value for. So when we want to estimate the value, I think I would like to name the parameters, so then it's easier to refer to them. So I would just go define name, and I say P, and my P is going to be E2, which is correct. And define another name, define name, and this is Q. Q is F2, this is correct. Next one, define name, N bar is G2. So I've defined all the names. If you go to name manager, you can see all the names here. Once I have all the names defined, then I want to find the predicted value using the BAS model. So in order to do that, I need to put in the formula in cell D7, D6, D5 up until D21. So actually this is gonna be just 0. The next thing is just gonna be equal to P, using this formula right here, the P times N bar minus C5, okay, and then plus Q times Q divided by N bar times C5 times N bar minus C5. All right, so this should be it. Okay, N bar, oh, I have to put the initial value for this. So let's just assume that P and Q is 0.5, 0.5, and maybe this is, I don't know, like 1,000. I'm sorry to mention something. In this formula though, P and Q have to be less than or equal to 1 and greater than or equal to 0. Okay, so this is the condition that you have to have in your constraint later on. So in this case, I just assume that P is 0.5 as well as Q is also 0.5. I assume that there are about 1,000 customers in the market. These values can change later once we use the solver. Okay, once you put in the formula, we can just copy the formula down like that. Okay, and then we can find the sum of the square error first. So the square error, this is just going to be that minus the true value, which is NT square. So you just do that, and you have all the square error. You also want to find the sum of square. So this is just going to be the sum of all these. We've done this so many times, so I really hope that you guys can do it now. Now, your sum of square error is like 3,800,000 or whatever. So this is like too much, way too much. This is huge. So we're going to go to data, solver, We want to minimize E3, which is correct. We want to minimize the sum of square error by choosing the parameter E2, F2, and G2. You specify the range for the parameters. First, our P, Q, and N bar has to be greater than or equal to 0. We also say that, you know, P and Q has to be less than or equal to 1. Actually, we need one more constraint that, you know, maybe N bar has to be less than or equals to, let me just put 20,000. We can change this later if we feel like we want to change something. So let's just try that. Okay, click OK. And then we use DRG nonlinear. We want to specify all the upper bounds and lower bounds for all the parameters so that we can use the DRG nonlinear. If we don't specify all the bounds, then DRG nonlinear cannot be applied. So now I'm just going to click solve. And now it said that solver has converged to the current solution. All constraints are satisfied. So we want to keep the solution and click OK. Now I got the estimate of the sum of square error to be, you know, 96.07. So this should be pretty close enough. Okay, well, still N bar is 999 something. So this is way too much. It's kind of weird that you get like 999 number of customers, but this is okay. One thing though that I want to point out is that the sum of square error that I got in here is a bit higher than the one in the textbook, but it should be okay. I think it really depends on the solver, because many times when you run the solver, you don't really start with the same initial value. And since this is the nonlinear programming, sometimes you're not gonna get the same solution, okay? But this is just something that, you know, we can definitely adjust a little bit. So when we say N bar is less than or equal to 20,000, this might be a little bit too large or too big of the range. Maybe we can tighten it up a little bit to say maybe this is, we want to limit to be less than or equal to 100 and see what happened, and then we want to solve it. And again, we also solve the program again. And for now, we got the solution to be less sum square error to be 74. This is pretty close to, oh, actually the solution is the same as in the textbook. So, you know, if you have a bigger range of the parameter or the changing cells, then it's really difficult for the program to find your solution. So the program might think that they have found a good enough solution, but if you tighten it down a little bit, this is kind of like cheating, because we already know the solution. So I know that N bar can be less than 100, so I try that. Once we try that, we get a better SSE. So running solver, sometimes it's not just about science, it's also about art, that you have to like specify the initial values or the initial bounds for all the parameters. In reality, you might not know, you might not have a better understanding about the bound. That's okay. We can try using the trial and errors. But since in this case, I knew a little bit about N bar, so I just said that maybe it can be less than 100. And voila, I got SSE to be, you know, pretty low, at least lower than what I had earlier. So this is good. So this is, you know, one way that you can do the estimation using the Bayes diffusion model. So this is the prediction for each period. So I'm just gonna end this method now, and then we can go do the next topic in the next clip.